For centuries, the simple act of lighting a candle posed a profound question in physics. We could see the sharp shadows it cast, but the actual physical substance of the light itself remained a mystery. By the 1700s, Isaac Newton had proposed a highly influential answer. In his book, Optics, he argued that light was composed of tiny, discrete particles, or corpuscles, traveling in straight lines. The Dutch physicist Christian Huygens offered a competing idea. He suggested light was actually a wave propagating through space, much like ripples moving across a pond. To settle the debate, scientists needed to observe interference. This is the specific physical phenomenon where two overlapping waves either add together to create a larger wave or pull against each other to cancel each other out entirely. The problem was that light moved at nearly 300 million meters per second. Its behavior was so rapid and chaotic that no instrument of the era could capture two light waves in the act of interfering. The debate sat unresolved for over 100 years. If you want to see light waves interfere, the most obvious approach is to place two separate lamps side by side, shine them through two pinholes, and look for a wave pattern on the wall. But if you actually run this test, you don't get a pattern. As this diagram shows, the overlapping light just creates a uniform, featureless blur. This flat illumination seemed to support the idea that light was made of particles just piling up on the screen. The real reason this test fails is a property called incoherence. An ordinary light source, like a sodium lamp or a candle, doesn't emit one steady wave. It undergoes abrupt, random phase changes in about 1/10 billionth of a second. Because the two lamps are independent, their wave emissions are disconnected. They are constantly falling out of step with each other, shifting rapidly and washing out any possible interference pattern before the human eye can register it. To prove the wave model, researchers needed to take two different light sources and lock them into a perfectly synchronized, stable rhythm. In 1801, the English physicist Thomas Young designed an apparatus specifically to force light into that state of perfect synchronization. Here's his setup. He passed light through a tiny pinhole, isolating a single expanding wave. A second screen with two close pinholes split that wave into two distinct sources. Born from the exact same ripple, they share the identical phase, remaining perfectly coherent. Young bypassed the erratic nature of the lamps entirely. He used geometry to tame the chaos of light, ensuring the waves maintain a constant relationship. When waves overlap, their physical displacements add together. Two wave crests arriving simultaneously combine to form a supercrest with double the amplitude. This is constructive interference, the physical cause of the bright bands. Conversely, if waves arrive exactly out of phase, the crest of one meeting the trough of the other, they pull in opposite directions. The displacements sum to zero. This destructive interference creates the dark gaps between bright bands. Looking at this formula, we can predict exactly where those bright fringes will appear. The position of each bright band depends on the wavelength, lambda, the distance to the screen, capital D, and the spacing between slits, lowercase d. These equations provided the mathematical framework necessary to prove that light behaves as a wave. This image displays the final, stable interference pattern produced by the experiment. These perfectly spaced vertical stripes of light and shadow provided the hard physical evidence the scientific world had been looking for. Because the math linked the spacing of these fringes to the properties of the light itself, Young was able to run the calculation in reverse. By measuring the distance between the bright stripes on the wall, he could calculate the actual wavelength of the light. The resulting measurements revealed an incredibly small scale. For yellow light, Young calculated the wavelength to be a mere 0.0006 millimeters. Because this wavelength is so minuscule compared to mirrors and lenses, light appears to travel in straight lines, hiding its wave nature from our daily observations. This repeating pattern is a signature restricted to waves. It is a spatial distribution that discrete particles, moving in straight lines, cannot produce. Armed with this evidence, the scientific community had to reevaluate everything. Newton's particle model, which had dominated physics for over a century, began to lose its hold. While some initial skeptics rejected Young's findings, his model made testable predictions. Experiments by Foucault in 1850 later confirmed that light moves slower in water, exactly as the wave model required. This experiment provided the data required to classify the electromagnetic spectrum, leading directly to the development of modern fiber optic communication. This shift in our understanding of the universe was achieved using two small holes and a single source of light. Thomas Young captured the locked phase relationship of light. By doing so, he allowed us to find